Hello and welcome to Vidoes Academy. Today we will learn how to make graphs with Python, and pretty much this is our input. In Jupyter notebook we have NetworkX as NX and of course pyplot as POT, and this is our data. This is our input for the graph. We have 19 edges and 21 nodes. And these are the edges here. So between A and B we have 1, and between O and P we have a value of 100. Then these are the nodes, and for each node we have heuristics of approximate, saying how far away are we from the goal. And in this case the start is A, the goal is P. If you stay with Vidoes Academy up to the end of the video, you would see something like this out of that, and pretty much this is the target of the video that we are trying to reach. So this is A, for example, and from A to B we see that we have a node, we have a one-way, and it's on the value of 1. B has a heuristics of 5 because of this here, and for example P has 0. And between F and P there is a way on the price of 50. You can find it probably somewhere here. F to P 50. This one is the heuristics. Okay, so far so good. This is what we are trying to reach. Once more showing it. It would be a bit better than this actually, because it would be in Jupyter notebook. And even if you take a look quickly here, we have X, Y, and Z. And they should be added somewhere because they are not related with the rest of the way, but they are still there. So this is a video like the first one of a series about graphs. There will be 4 or more other videos where breadth first search, depth first search, A*, beam search would be presented, and we will always be using this figure with this graph. So let's press Shift and Enter and see what we have. Well, it is something. What can we do? This data can be split into lines with data strip and then split. Let's see. Strip is the way. What about now lines? Well, we have to say that we want to split by a new line, and the sign for new line, pretty sure you all know it, is n/n. So this is how it looks. And now let's read the important part. Header is what we want. So header is lines 0, and I'm just splitting it. And header looks like this, 19 and 21. So we have 19 edges and 21 nodes by design. Yeah, let's say number of nodes would be int header 0, and number of edges would be int header 1. That's how it is. Number of edges times 2, 42. Yes. Let me see how to then move it back. Okay. So we have this and that. Now we need to slice into the lists. Edge lines should be something like the lines from 1 to 1 plus 5. Let's see first what is this going to give us. So it gives us everything up to EF1, but we start from AB1. AB1 to EF1, great. So what about plus number of edges? YZ5 is the last one, YZ5 here is the last one. Then we go into the heuristics. Okay, that's fair enough. So this is the edge lines, and for node lines we can use something else. What can we use? We can use again lines starting from 1 and ending from number of edges, and just not using the last one, I guess. xy5 is good, so it should be 1 plus number of edges, oh no, 1 plus number of edges, and up to the end. So we start from A50, and we don't need A and P because A and P are our start and end, so to say, go and finish. So we need to say minus the last one, and it actually works. So this would be our node lines, and this is how we get them. Okay, make the code a bit better, put everything in the same cell, delete everything else, and see whether everything looks okay. Okay, so now the last one was lines -1 and P. Great. So if we split it, it will be split by space automatically, and this one returns automatically a list. So if we want just the A, this is what we got, and this would be start node, and we should have also end node, so to say. This actually has a not so good thing because we are doing this one twice, but as far as it's actually minimal calculation, we are quite happy and quite okay with it. Okay, so far so good. We have everything here, and we should be happy. Okay, now let's build our graph structure. We want to turn pretty much these lines of text into connections, and let's give it a try and see what we can do. So first, let's declare our ng nx DiGraph, and it will be called G. Let's see what we got. It's NetworkX classes DiGraph ggraph at something. Great. And now I want to be able to make some kind of print and to assign something of these things here into the graph, something like edge lines, these ones, and I'm going to do it with a loop, and the loop would be for line in edge lines, print line. Well, it works. And just double checking again, we're starting with AB1 to X to YZ5, AB1 to YZ5. These are the edges. I'm going to show you probably once more the picture, but I somehow lost it, so you get what I want. Yeah, we've printed it, and now let's say we have parts called line.split. We can say print parts. Let's see what we're gonna say. Okay, great. We made lists from just line.split. So the first one is from, the second one is to, and the third one is the value. And let's name them like this. U and V are the standard ways of naming things in Python, especially for graph. And V or W for weight, so to say, it would be int parts 2. Let's say print W, just to see whether everything's okay. Yeah, perfect. So we have U, V, and W for every one of our edges. And now let's use the magic code g dot add edge. And here we can say u, v, shift and tab just to see how it's happening, u of edge, v of edge, an additional attribute. Additional attribute is keyword arguments optional. I'm just looking somewhere what it is going to say. Okay, it's about weight. Yeah, obviously. And we also have capacity and we have length. Wow. You can do a lot of things with this DiGraph. In our case, it would be weight equals W. Or we can simply name it W because it was the third one coming, but let's keep it like this. Yeah. We can say something like print link established, link between, and I'm just thinking here, U, V, W. Would it work? If it won't, I'll make it better. Probably something like this. Okay, probably something like this. And something like this. Yes, it works. Great. I'm really happy that these things with the comma works. In VBA, you wouldn't see it like that, but yeah, don't compare Python with VBA. And let's continue adding the heuristics. So we add the age value to the nodes, and this is it. And the idea is that this one is, as noticed before, would be in general problem. This could be like the expected value to reach from the given node to the endpoint, which in our case is P. Let's give it a try. First of all, how did we named our node? It was node lines like this, and obviously from A it is 50, and from P it is 0 because this is our target. Okay, let's try to put a loop. If you are hardcore Python developers, you're probably unhappy to see me looping like this. Let's see what the parts are. The last one is at 77, okay. But yeah, what can we do? So node is parts 0, and we have the heuristics value equal to parts 1, and it's also an integer. The last heuristics value should be 77. Great, the last node should be Z. Everything's perfect. Yeah. Or at least we think so. Okay, let's add the heuristics somehow to the G. I'll add it here in the loop G add node. Oh no, it's not G add node, it should be G dot nodes, and then node. Yeah. And the node should be having an H, and it would be H value. And it should be like this. Great, let's see how it works. Yeah, it works. And if it is not this one, but let's say I, we should be getting 40 or something. Yes, okay. Our thing works actually. What can be better? I mean, we have the G, we have this structure of NetworkX classes, DiGraph ready. It works for us, and this is good. Now let's go for the next step. we need to calculate the layer of every node, so the graph flows pretty much left to right. And yeah, the output should be a column showing where each node should sit in. So let's declare a dictionary. This is the way to do it. Or we can simply say dict. But this one is better. Just to show you what is it. Yeah, great. What do we do now for n in g.nodes? And of course column layers n equals 0. That's cool. Let's see what print n is exactly. Yeah, the nodes. What else? What were we expecting actually? I don't know. Okay, so we just made layers here that said, okay, this one is on the 0th level, which is good. And now we need some kind of topological sort that ensures that we process the parents before the children. And of course, Python has a function for this. So it's going to be called sorted nodes, and it's list.nx topological sort of G. Let's see what we have here. Oh yeah, A, then X, then everything else, then P. Pretty much that's kind of good. That's pretty good. Let's continue. So for node in sorted nodes, the good thing is that they are really sorted, so no worries. Current depth equals layers node. I think it should be 0 everywhere. That's good. But now the interesting part comes. So for child in G dot, I'm just pressing tab, successors of the node. Here we can say if layers of the child is less than current depth plus 1, then increment it a bit. Okay, just to show you this one, for example. And if we want to see the successors of A, it doesn't work like this. G successors A, dictionary key iterator. I'm just thinking, okay, let's see what attributes it has. No, not these ones. Okay, so after some time we found what to do. The answer is, if we want to see the successors of A, we do list G successors of A. Then if we want to see the successors of B, we go like this. And this OS comes from G, which is coming from here, NX and DiGraph, so to say, which is great. Actually, I'm going to leave this line here, so we know what we are doing, or at least you know what I'm doing, or I know whatever everyone is doing. Yeah. So we have the layers. Let's see how it looks like. Yeah. This one actually has provided us some interesting findings. For example, P Is it the Go? It has the layer of 9, O has the layer of 8, and A is the layer of 0. So A would be on the left of your screen, P would be on the right of your screen, and between them there would be like a few other layers of other numbers. This is how we are going to do it. Okay. Yeah. Now let's apply this one to the graph, so to say, for node and depth in layers. Items. Let's see what we have in layers. Okay. Node would be this one, depth would be that one. Just to see whether we do it correctly. Yeah. So this is what happens if you loop a dictionary. First it gets the key, then it gets the value. For those who haven't done it, in my case, I sometimes forget a lot of useful stuff. Subset equals depth. Okay. So let's see, G nodes. That's good. And then let's take node B. And you see that it somehow says subset equals 1. We can say also here G nodes node, and we can say here like Vidoes Academy, and give it value depth by 7. And yeah, somehow it works. Yeah, this is pretty much nice dictionary object. Or it's not dictionary, it's probably, yeah, depends on how you call it. It can be hash map. Not sure how it is called in Python or something like this, but you know my point. Okay, let's continue, and now let's go to the visualization, which actually is the most important part. Okay, so first we're going to calculate the positions. So something like something like this, multi-pag layout. Yes, so G subset keys would be from our subset. I'll just put it here, and this one would be G nodes, I think P. So this is the position. And what else do we need? We need to have, should we put some colors or not? That's a good one. That's a good one, probably not. And let me think how to do it better. Let's start plotting the stuff. POT figure is good. Fixed size. Our favorite tuple for fixed size is 14 by 8. And NX draw network nodes. Wow, it actually has its own library. And we say G position node color equals node colors. I'm going to define it here. Node colors, node size 1500, edge color, edge colors would be nothing about black, and that should be okay. So PLT show. Now about the colors, just thinking, let's have something like green. Green is good, and green is something like 19E, and I think should be something like 090. Yeah, let's try. PLT show is invalid syntax, of course. Yeah, always like it. I'm just thinking, okay, why it doesn't like the PLT show? Invalid syntax. Unexpected EOF when parsing. Okay, now I guess it's this one here. Yeah. Okay, each colors. Each color should be a bit different. I'm just thinking how to do it. Node colors. Okay, let's do it the classic way. The node colors will be called here, and they will be an empty list. And now we'll say for n in G nodes. Pretty much the idea is that every time we say something, the node color will be different. So if n equals start node, and our start node was A, so just not forget. Node colors dot append, and we said we're gonna have green here. I think I knew the green one by heart. 90E 090. Don't ask me why I know this one. And then elif n equals end node, then node color append, and here we would be having something like ff, and it's red, green, blue, so I'm just thinking, okay, something like this should be, I guess, enough. And then else node colors append, they will be blue, so red, green, blue, or I'm completely mistaken, doesn't matter. And this should be enough. Okay. What it doesn't like draw network nodes got an unexpected key argument, not colors. That's interesting. Let me check. Why do I get this mistake? We have the G, we have the position, and we have the node color equaling node colors. These are the node colors, it's perfect. What? Why is it complaining? Draw NetworkX nodes. We get the G, we get, okay, let's press Shift and Enter, see what it is complaining. Node color. Okay. Let's use this one. Okay, and now it is about the edge color. And what is it about now? Okay, I'm going to remove this one completely, and now we got it. Great. This is what I was hoping to get. Yeah, as you see, we have obviously two on the same line, which is not that bad. We see everything is blue. Because we're missing this one here. Yeah. The green one is missing somehow. Let's make it a bit more interesting. Okay, and start node, end node. Yeah. Okay, node color, we have this one, and it's for everything. I don't like it this way, but yeah, great, we got it. We got what we hoped for. We have the green, we have the blue, and we have the red. And what else? Yeah, we are doing good. Okay, the blue one is actually a bit too blue. Let's make it something like this. Okay, taking my words back, something like this, and then something like this. Well, that's probably better. I mean, it's blue. Yeah, and let's continue with writing stuff or fixing the blue a bit. I'm thinking about here or nah, that's very not blue. Okay, this probably looks okay. I'll probably fix the values later just to make it more appealing to everyone. Okay, so now we need to build the connections. That's the good one. Let's add the edges here. NX draw underscore network edges, and we say we have G, we have position, we have edge color. It's gonna be gray. Because I like gray and I don't have to think about it. Arrow size would be 20, and it works. Somehow not bad. Let's see what will happen here if we say append blue. No. End node would be append red. And the start node would be orange. Actually, yeah, it works. Even we have one that is like that. Let's try to find a way to separate it, made it a bit different. Okay, somewhere here, a leaf and in. Okay, I just know that they are like that, so That's the easiest way. Node colors, append, and the color would be purple. Yeah, you see this one are completely separated from ours. This one is not the best. I'm just going to comment it out because the idea is that the code should be reusable, and here this hard coding is not good, not the best thing I could have thought of. Okay, so far so good. We have done the connections. Let's put a title. POT title would be graph. It would be the graph. No relation to Rammstein or whatever. There was a song about it, or the X, I'm not sure. Let's add the node labels with heuristics. Actually, not with the heuristics. Pretty much we're gonna add these ones here. So the one between F and P would be 50. And let's find a way to build it within. So NX draw. Yeah, draw NetworkX labels actually works great. So we have the G, we have the position, the labels, node, have node labels, and font size should be 8. And I'm not sure that we have something declared as node labels. No, we do not. So let's think how to define node labels. Yeah. Where are we going to define them? Actually there. So node labels should be a dictionary like this, and pretty much we should be going here and here. So for n in G nodes, and here we'll be saying heuristics value would be G nodes and get H or get question mark if there is no, and then the node labels, come on, for this n would be equal to something like this. And then probably a new line. I'm just imagining it or not. H value. Yeah, the imagination wasn't good enough. Okay. And this one is not needed. Here. Let's see the node labels for A, how it would look like. Yeah, A and then 50. And the one for P should be 0. That's great. Okay, the node labels are there. Labels, node labels. It's not happy because of something. Probably the name node labels wasn't correct. Unexpected keyword argument labels. Really? Like the draw NetworkX edge labels got an unexpected argument. Okay, probably called edge labels. Nope, edge labels doesn't support multi-edges. Let's first see whether or not labels actually made something. Okay, made, yeah. Okay, so shift and enter. Edge labels none. And let's see label position float. Each labels in a dictionary of labels. I'm just thinking about foo, but it doesn't want to be foo. And this is interesting. Should be having a labels and not labels. Okay, I'm just thinking, what if I do it like this? Unexpected keyword argument labels. That's unfair. Draw NetworkX edge labels. Okay, so the word is not edge labels, but just labels. And labels should be no labels. And this is an example of why we should not be making our own colors. The blue is too dark, so it should be, not sure whether this color exists, light blue. Obviously not. Yeah, this one's good. So we are somewhere. We have the labels, and now we have to write the edge labels, which is what I was hoping to make here now. And do we have edge labels? That's another question. Nope, we don't have edge labels, but we're gonna define them on the same place where we define the not labels. It's gonna be edge labels like this. And the edge labels would be defined with a loop. Pretty much it would be with the weight, I think, yeah. Or we can do it a bit differently. We can do it with nx dot get each attribute, and then g, and then weight. Let's see. Fair enough. So for each one it got the edge. What if for each one it got the vidoes academy? Yeah, okay, this wasn't there. This was one of the official attributes, okay. Where were we? Yep, we were on the NX draw network. And then it was draw network edges or draw network labels. Draw network edge labels. This one's, so we had the G, the positions, the edge label, And then we have the font size. And I think I should have generated this once more so the weight is there. Yep, exactly. We have 50, 2, 1, 1, and everything looks pretty much okay. So far so good. Let's recap on what we actually did. Starting quickly, we have imported two important libraries. Then we have added our data, a few stories with lines, header, and nodes, edge lines, node lines, start node, and end node from the data actually. So this way we were able to generate it nicely. G is pretty much the object that we are using, DiGraph, and then we started for line in node lines. Everything works. Yeah. And then at the end we have the graph like this. And we have one separated graph here with X, Y, and Z, which actually works pretty much okay. I would say, just reminding you that this video is the first one of the series for graphs and graphs traversing. The next one will be with DFS or GFS, depending on what I do. But I will be using pretty much this exact graph, so we get some idea about what is going on and how do we do it. So I hope to make this video as well. So I hope you like this one. Thank you once again for staying with me and enjoy the rest of your day. Goodbye.